I'm starting a little bit to. I've been kind of going back and forth. So my sort of preset schedule is to start at 8 a.m. and go till 11 a.m. for the morning session, and then from 2 p.m. till 5 p.m. for the afternoon session, giving me some time to have lunch and do some work in between. Now, it hasn't turned out exactly that way because I've done more than that for a number of days, particularly this week. I did a few where it was basically 7 a.m. till 6 p.m. with just a short break in between. And this was because the class is hard and I wanted to make good progress so that I can be in the state that I'm at now, or have a bit more time to do the kind of work that I need to do to understand quantum mechanics, or at least to the level of 804 at MIT's class before the project concludes the end of April. Now, today was a little bit rough. I'm cat sitting, which anyone who's been following it has maybe seen this cat come in and out of the feed at random times. And today, for instance, the cat decided that 4 a.m. was a good time to wake me up. And so I'm a little bit hazy, a little bit fuzzy today. I wasn't sleeping super well. So I'm hoping that that's not going to cause huge problems. Sleep is obviously very important, not just for having energy and being able to do things, but particularly for learning. In particular, the kind of deep sleep that happens in the beginning of the nighttime is very important for memory consolidation. Although REM sleep, which tends to come a little bit later as you start getting into the later hours of the morning, is also important for aspects of memory and aspects of your emotional state and things like that. And so the fact that I'm kind of missing that last little bit is not good. I don't like to miss sleep, but sometimes you can't avoid it. What I'm probably going to do is just keep working on it today. If I'm feeling like it's a real grind because I'm missing a bit of sleep, then I might take a nap during that kind of break period and when I come back, which is always good. I think sometimes people think naps are a sign of laziness. You're napping instead of really working. But for learning, sleep is really a complement of the actual activity of studying. That if you do a bunch of learning but you cut sleep, it's like trying to be a bodybuilder gaining muscle and you stop eating food. Like, you do need to do the exercise, the workout, the kind of strenuous part, but you need to give yourself the fuel to grow. And for learning, that fuel is very often sleep. So we'll see how it goes today. I generally recommend, if you're in a situation where you didn't sleep that well, this kind of thing, to still try to put in what you can towards your schedule. I think it's important to separate kind of what works best in any given moment with the kind of motivational consequences of giving yourself infinite flexibility. So if you just sort of let yourself, decide on a whim whether or not you feel like studying, it's not going to happen a lot. And I have been really enjoying this class. I think it's really interesting. I'd like to maybe at some point move on and do 805, 806, quantum field theory. Like, these are all subjects that I'd like to go further in. But in every particular moment, it's hard work learning. Like, in any particular moment when I'm studying, when I'm learning something, it's confusing, it's frustrating, it's difficult. And so this kind of high level, I like doing this, I'm interested in this, this is fascinating. And the low level, learning is hard, learning is frustrating. It can be difficult work sometimes. Those sort of simultaneous levels mean that if you give yourself too much flexibility at the low level, you very often let your short-term frustrations override your long-term goals or the things that you want to accomplish. And so for me, I'm going to try to work today and stick to my plan, even though I'm maybe not in the ideal state for studying. So I finished all of the lectures and first pass on all the problem sets. First pass meaning that I've done almost all of the questions in the problem set. There's a few that got omitted for various reasons, but basically finished all the problem sets. So with these two things combined, I can say with great confidence that I have seen and practiced all the material. So it's no longer a case that when I just finished the lectures, I've seen most of the material, although in this particular class, there's a lot of concepts that actually they introduce in the problem sets that are separate from what they introduce in class. Like, you will show this in the problem sets, but there's no explanation for it in the class, and you're supposed to do it in the problem sets. So unlike some classes where the kind of material covered overlaps, there is actually some divergence here. But that being said, I've now seen all the material and I've practiced all the material. So what I'm doing now over the next several days that I have left in April to work on this project is just trying to get myself to fix as many weak points as possible. And I'm going to be doing a mix of, I'm going to say Feynman technique for this approach, but it's really a little bit more than just Feynman technique. Some of it is going to be rewatching particular lectures. Some of it's going to be making sheets. So it's sort of a mix of different tactics. But I made this sheet yesterday. So I made this sheet. You know what? I'll just switch to the, why not take advantage of the fact that I have a second camera here. So I made this sheet yesterday, which you can just barely fits in the screen here. And this sheet has two sections. So the top part is a list of problems from the problem set that I decided I would like to redo. So this is a more selective pass. So things that I omitted, questions that I got right, and I also omitted questions that I got wrong, but for trivial reasons, meaning like I forgot something kind of obvious on it, which those things matter. I don't want to claim that they don't matter, but it's probably not worth going through the whole problem again if it was like, oh, I forgot that, you know, this is going to be factor of 2, or this is going to be a square root, or, oh, you know, like I said that there's no uncertainty in the momentum, but there's actually, it could be, there's two different ways it could be going. So these are important ideas, and I don't want to discount those kind of errors, because obviously that can make a big difference if you're making lots of those mistakes on exam, but they're not going to benefit much from practice. Whereas the questions I want to benefit from practice are questions that I got those questions wrong, and so I want to try doing them again. And there is a worry. I was doing a little bit of an analysis yesterday about if you over practice a specific set of problems, especially if they're randomly drawn from some subset of total problems that you could be expected to know, you will, in some senses, over practice the wrong things. So I just kind of use this diagram here to show, like, let's imagine this big circle is all the possible problems that one would be expected to solve given this knowledge, so that someone who's taken 804 should be able to solve everything in this white circle. And this white circle would be some kind of, an exam would potentially be some sampling of this. Now, the actual problem set is presumably some subset of these larger set of problems. Now, the ratio between these two is very important. I have a lot of problems, so I'm thinking that this is actually fairly large in this possible problem set, especially if we consider the possible problems that could appear on the exam. Then I would say that it's actually quite large indeed. But the problem is that if you keep practicing the same set of problems, then you will eventually memorize these actual problems, but you are going to not get better at all the ones that are not covered under here. So one way to think about this as well, as I was saying, is to think about ideas being taught in a class as being part of a hierarchy. So at the top, you have high-level principles and concepts, particularly for physics, but math and stuff, and this is true. And then as you go further down, you're dealing with more and more specific techniques that were for solving very specific problems in specific ways. So the trick to solve a particular problem of, you know, you need to do this particular commutator relation, that's the trick to solve this particular problem, is getting further. And then you get down to just answers. And so obviously you can understand at these two levels that if you just memorize that the answer to this exact problem is 7, that's not going to be very helpful for you because if they change the number slightly, you're not going to know how to calculate it. In contrast, if you only understand things at a very high level, but you don't have any technical mastery, then it's often just not possible to have a deep enough understanding here to just rederive how you would solve everything from this conceptual level. So what I'm trying to do right now is trying to pick the right level of scope for covering these problems. I don't want to go too fine-grained in the analysis because then I'm going to be missing the details. I also don't want to be going too high level. So I'm doing Feynman techniques of just high level stuff, because then if I'm just doing high level stuff, I might miss a lot of the little details that are necessary to solve problems, particularly for the amount of time that I have to cover. So Dylan is saying it's like overtraining for ML and AI. Well, I think that's absolutely right. That a lot of machine learning is related to actual learning in this way. That if you can think in terms of machine learning that this is your training set, and this is your set of, your possible sets that you can be examined on. So if you overtrain this set, you will overfit this data and not necessarily fit this one. Overfitting is less of a problem in actual learning, just because Generally, it's not the case that we have overly complicated models for how we process things, but there's an analogy there, definitely, in terms of what you want to do to learn. So these questions that I'm going to be working on is I've got these questions up here, and I've got these ideas to work on. I already started working on some ideas, particularly I was working on, let me see if I can cross it off. I don't know whether it neatly fit into this. I think it was interpretation of the phase, which I don't think I wrote down on this sheet, but it was on the other one. Oh yeah, phase of T are meanings of this. This I've done. So I'm not going to be able to cover all of these probably, but I'm going to try to cover some of them. And I like to split them into concepts, facts, and skills. These are blurry. I don't want to make it any case that these are sharp categories, but the way I like to think about it is not in terms of so much, you know, is ontologically such and such a concept versus a skill, but rather what would be the way to get better at it. So these are very much utilitarian categories that I'm using here. So concepts are things that you get better at by understanding them. Facts, you get better at them by memorizing them. Skills, you get better at them by practicing them. And so there are things that are skills and concepts. But definitely things that, okay, I understand that, but can I do that, you know, quickly and accurately on an exam? That's the skill category. So I have things like techniques for solving problems, integrating by parts, dimensional analysis, you know, using symmetry to cancel dot products. Whereas these concepts are less about a particular technique, but more understanding at a high level, you know, what's the deal with identical particles, or what does the crystal momentum mean? And this is where I'm trying to get analogies, visual representations, this kind of thing. Facts, these are more things that just need to be memorized. I've written down a bunch of things here. What I'm probably going to do for this, I might do this today. I might do this now, actually, because this is going to be something I'm going to want to test more than once. It doesn't take long to test, but I want to test it more than once. And so what I'm seeing here is that we've got this is the sleepiness coming in. What I've got here is all the things that, you know, it would just be useful to have these memorized. So some of those things are various relations of different operators for different systems. So for instance, some of the problems we've solved have recognized the fact that the energy operator is this raising and lowering operator applied plus 1/2 omega h bar, or the, you know, this number operator, or, you know, A is equal to, you know, the momentum by momentum naught. Like if you know these things, it's going to be a lot easier to solve problems, because it'll be like, you know, as you know from this formula. I'm going less strong on this than I could, just because for exams, I do have this formula sheet. So I'm not going to memorize any formula that appears on this sheet. I should put it under here. But I printed this off from one of the exams. So this does not have everything. So I'm going to focus on things that are not on here. But various operators here, units. So knowing, you know, what would the units of this be? What would the units of that be? What would they, like, having those memorized so that I can do dimensional analysis quickly. Things like, you know, time evolution of the, is this e to the I, et over h bar, like making sure that I have that. Integrals of Gaussians, trig identities. These things were coming up again and again and again. Someone's asking, is there any way that I can turn off these daily quantum mechanics notifications? I'm not sure how to do that, to be honest with you. If you can find out how I can turn it off, I would like it. I agree, having the live videos all the time is probably a little bit annoying for some people. It's a hard challenge because I'm doing it all the time for this, but at the same time, it can be a bit frustrating because it distracts people from the rest of my content, which is not so voluminous and necessarily like this. But I made the mistake in the past of separating out my content into other channels, and then it was really hard because you can't reintegrate them. You can't bring them back. So I have a channel for the MIT Challenge, channel for the Year Without English. And so I wanted to do everything in one place, but you're right. It is hard to do this live stream. If this becomes a thing and it becomes a hard thing, I might switch to a different platform for doing a live stream. So I might do Twitch for live stream, and then, you know, publish some highlights to YouTube. I have to decide, but for right now, I'm doing it through YouTube. So I apologize, Namate, about the constant Scott is now live updates for my channel. So the basic idea here is that I want to work on these facts. I want to work on these skills and concepts. So for these facts, I might just make a sheet right now that just puts all this stuff out there so that I have like a basic understanding of this and I can just test myself throughout the next several days. For skills, I think for these, even though there are skills, I think I'm probably going to do something like a Feynman technique for them. And because I'm going to be practicing again in these questions. And these questions up here are going to be an important part of the work too. So what I'm going to do for the rest of the day is work on this part down here. I'm going to work on this all today. And then for the next, I want to have 2 days. So I'm going to say for the next week, I'm going to probably alternate doing this and this. So I haven't decided whether I want to do like 1 day problem set, 1 day this. Probably I'll do like morning, afternoon. So I might do morning problem set, afternoon this. This tends to be a little bit less intensive. And this tends to be a little bit more on the questions. Yeah, no worries, mate. There's no need to apologize. I do realize that, you know, most people are not going to want to watch every single second of this project, but I wanted to do a project where everything was documented, every single thing was, so that there was nothing missing. So obviously, I don't expect people to see it the whole time. My original idea behind this live stream is that it would just be kind of going on in the background, and you know, if people wanted, they could just check in at various points to see where I'm doing it. I didn't realize that YouTube was going to give a notification every single time I go online. That's not ideal. So maybe there's a way around it. Maybe I can make it so that I'm not having my notifications go out for the live streaming. Who knows? YouTube can be a little bit frustrating, but you're right. I might do Twitch in the future for projects like this. Twitch is pretty popular for live streaming. I've had some issues with this live streaming software because live streaming software tends to be engineered for Twitch and not YouTube, and so we were having some connection issues. But for the rest of this project, it's only another week and a half. I'll be doing it like this. So with that said, I think what I'm going to do is work on creating this facts list right here. And I think I'm going to do this. I'm trying to think of how I want to do this. Because what I want to do is I want to be able to do it with active practice. I don't know whether I want to do flashcards. You know what, why not? Why not? Let's do flashcards, because if I do flashcards, I should be able to just keep those separate and I can just run through them more quickly. I'm going to do actual flashcards. One thing you can do is Anki for like, if you want to do spaced repetition. There's not really much benefit of doing that at this point because I only have about like a week left. So if you are doing flashcards and you're going to be doing it over the whole semester, that might be valuable. But this is a month-long project, so the spacing repetition thing is not going to be truly valuable. And the amount of flashcards I'm dealing with is not large. So given that it's not large, I'm thinking that, you know, paper flashcards are going to be a bit easier than trying to set up it on Anki and then, you know, playing with it here. So I'm going to go look around for some note cards. If I can't find some note cards, I will just cut up some paper, but I'll be back in a sec. So I wasn't able to find any blank note cards, but I don't need that many. So what I'm going to do is just use some of this regular computer paper, and I will just cut it and fold it over so that I can make little cards. All right. These don't have to be fancy. I mean, flashcards are just flashcards. Yeah, if I had them, I prefer the little index cards because they're a little bit stiffer, a bit easier to flip through like deck of cards, but these are fine too. And you know what, maybe I'll just do, yeah, I'll just do this. Okay. And I think I want to just have different colors on each side, so I will do maybe, what do I want to do? Do I have a different colored pen? Do I have a blue pen? Is this blue? Is this black? No, that's also black. Oh, this pen doesn't look very good though. This pen is blue? Okay, blue. Just so that I know which one's which. So let's go through and put some things down. So I'm going to put so I'm going to do blue for the question. I'll put question in front too. So let's go. So units of psi of x. Oh, you know what? I'm just thinking these might not be thick enough. I might be able to see through them. Yeah, I can definitely see through them. So you know what? I'm going to fold them in half. And then that'll make them a little bit easier to, might be too many. I'm going to do this many. My Brazilian friends are watching me. Do I have any tape so these don't? Oh, I do have some tape. So I know you guys haven't come here for arts and crafts, but this should only take a few seconds. And then I'll have some nice little flashcards to work on some of these things. There's not a lot of memorization to do in this class, but I'd like to have some of the forms memorized, and it will be just good to recall this. Oh, Cat's here. Hello, Cat. You've been keeping me up all night. Now you've come to join my live stream, hey? Okay. All right. All right. I mean, these are a little bit, you know, a little bit Bush League flashcards here. I'm sure you could go out and buy better ones, but I didn't want to waste time. And I didn't want it to be too visible on the other side what is on there. I think I'll use pencil too. This pen is like super dark, so I'm going to see it through the other side. Flashcards don't work if you can see them, hey? All right. I didn't do a lot of flashcards during the MIT challenge, so I don't want to say that this is a necessary process, particularly for math or physics classes. The only reason I'm doing this is just because when I was doing the problem sets, I noticed that I had to look a lot of things up that were not given on the problem set. Now, part of that might just be because they actually didn't include a lot of those things on the problem set, because the understanding is that it's open book and that you can look it up. But I don't really want to risk it too much because it's always hard to know what's going to be, you know, oh, you should just know this versus, you know, we're not going to expect you to know this closed book. So they do give a formula sheet. So I'm not going to put stuff from there, but I will put some other stuff just so that I can, get it. So I'll go through and I'll make these quickly. So we got some here, got some flashcards here. Is it the time zone? Is that why I've got so many people from Brazil right now? All right. So let's do pencil and question. All right, so this is going to be and this one here is going to be 1 over root. I'm going to say, I'm going to use meters just because. Sometimes it can be very confusing for math. Yes, that is opaque. Okay. So what are some of the other ones I wanted to have here? 2 L's per oscillator. I'm not sure. That doesn't look right. And so this is A bar A. So let me just get my. Is this one on here? I don't think this one's on here. Do I have? So A is our lowering operator and A bar is our raising operator. So that's going to be, I'm going to do it with that pen now. I think that's right. Yeah. Okay. What else do I want? I want so where I'm just going to get my notes here. Oh, this one's on the formula sheet, so I don't know whether I need this one. Yeah, this one I don't know whether I need. Let me go through actually and just do. Oops. Should have a bit of a better list of which ones I want to work on. Oh, wrong book. Haven't worked in that one. There we go. Let's do a few. think they have, yeah, they have H bar here, so I don't need that. This is kilograms times meters squared divided by second. Okay. Other things I want. What do I think is the relationship between biology and quantum mechanics? Well, everything is made out of quantum things, right? Like, so when we're dealing with molecular biology, there's a lot of stuff that quantum mechanics plays a role. So things like protein folding and, you know, DNA and basically all the actions of the molecules are quantum mechanical. So for a lot of effects, you can ignore that, or you can abstract it away, just how we abstract it away when dealing with everyday life, even though everything is based on quantum mechanics. But at some levels, you can't when you deal with things that are too small. So I'm going to go through here. So I want... This is de Broglie relation. Let me just switch over here. I want to write some of these down. Oh, no. So let me just look up. H bar M so What do you plan on doing with learning quantum mechanics? So I don't know whether there's something to be done with it. This is a more theoretical subject, so I definitely I don't see any particular use of it right now. However, it's one of those subjects that I think is important for understanding other subjects. So things in chemistry, quantum computing, things like this are worth subjects that I was interested in, and I couldn't understand it because I didn't have this math background. So this one is so h divided by 2 pi. So h bar is what? H bar is h divided by 2 pi. So it's going to be 2 pi h bar over so that's 1. And I also want it in terms of energy. I don't think quantum mechanics has anything to do with free will. I've written actually about that on my blog where I talk about how the problem is that free will is not really a fundamental category of the universe. It's a complex concept. So I don't think you can find it by looking in fundamental physics. If we have something like free will, it's an emergent thing that comes up at a much higher level of category than whatever's happening at the level of subatomic particles. So what should I be able to get for this? I should be able to do it with I practice meditation every day. I do not practice my Portuguese quite as often, but boa sorte and aprending inglês. Where am I here? I want to do what do I need to do to know the wavelength? I need the energy and what else? So I'm not sure what's the right way to calculate, because I always assume that you would need to know the angular frequency. So once we know energy, we should know the frequency. I guess I need the speed though. Yeah, I'm not gonna do this card. I'll leave this one here because I do need the speed for that. Leave some of these blank ones here. What other ones do I want to break down? I don't want to do too many flashcards. I think there's a risk of just memorizing stuff when you don't. I think, what do we have? Do we have basic operators here? Yep. Yep, those are there. There's a lot of stuff on this formula sheet. I think there was stuff relating to specific problems that were not on the formula sheet. So I'm going to put some. I think it's length divided by equal to, where is my G naught? I think I have that in the I don't think I have any for G naught here. I did it where I had this well. It's hard to flip through here sometimes. I remember drawing. Yeah. we're drawing the delta function. Where was the delta function barrier? Oh, this is too far. You know, it's crazy. I totally remember writing this down, but now I can't see it in my notes. Now it has to be after this. Oh. I'm looking for a very particular drawing I drew that I know I drew with pen and pencil that had the delta function. I think it was the dual. Is it later than this? I'm just going to go backwards from the thing that might be. Here. G naught. I have G naught here, G naught, G naught. This is in the context of the crystal momentum. Here? Where is it? I must have done it here then. So many pages here of notes. It's hard to find things through them. I have G naught here. Maybe I can look it up here. H bar over 2 MV naught. So just quickly working that out. I just hate to write down a mistaken. Thanks, Rodrigo. I can't find the thing I was looking for, but maybe I'm just going crazy right now. So that's L over H bar 2 MV naught equal to L Okay. Got that one. I think I'm going to just add a few trig stuff, maybe. I don't think I need that much more in terms of constants and things like that. Oh, I wanted to add some of the eigenvalues of the do I have it here? I wanted to add no, I've got this here. Where's the eigenfunctions of angular momentum? Let's go back to that. Now I'm going to leave those blank right now. Maybe I'll write these in. Okay. I didn't write this very well, did I? I think this is sine theta. Yeah, sine theta. Yeah, you know what? This is too complicated. I don't think they're going to expect us to remember that. I'll just leave this one here. You know what? I'm not going to do any more right now. I'm going to just leave my flashcards up here. And what I'm going to do is if I encounter stuff that needs memorizing, I'm going to do it rather than hunting through this whole book, just because I think that's going to cause its own issues. Eigenfunctions, yeah, I think it's okay. So I'll leave this like this for now. I was gonna do them earlier so I have more time to practice, but I think honestly I'm gonna waste more time digging around for things to write down than to just write it down as I go through problem sets over the next few days, even if I miss a few repetitions because of that. So what I'm gonna work on now, I think is, well, let's maybe go through this list and see what I want to work on. So I've left this for right now. There was a few of these that I was going to put in here, but I didn't. Let me just cross the ones that I've done. So I did this. Yeah, so I think I'm going to work on these skills because I want to do these skills before I get to doing problem sets again, because that's going to be the most direct thing that needs practicing. So I'll work on these now. Actually, what I did is I downloaded a few lectures from MIT that are of different classes that deal with issues that are on this list. So I think what I'll do is I'll maybe go through those right now to learn them, just because one of them is from 803, so the dispersal relation, which is here, which I'm going to go over. I don't know whether it's going to be super important, but I want to go over it just because I've never learned it. And then I also want to go through a couple things from calculus here in the skills section. So let me just put this off to the side right now. And I think I'm going to start with the dispersal relation. Okay, where's the blank page here? And I'm going to just, I think I'm going to just watch it first and then do a little bit of a climbing technique. So let me, and I want to go to other classes. Oh, only 2 of these downloaded. That's unfortunate. What happened here? Matter waves. Well, I downloaded other ones, but they don't appear to be here. You know what? I'm going to try downloading them anyways, just because I don't want it to, so let me just get those ones. Because I thought last night, you know what? I'm going to go over and look at some of these things. I don't know why they didn't download. I watched them download. So I wanted to I have Taylor series and trig integrals, and I wanted to do integrating by parts. Integrating by parts. And inverse substitution. So let's download this one. I like to download them. Oh, these were canceled. I don't. All right. That's annoying. And then I also wanted to download. This is integrating by parts. I want to download inverse substitution. So these are just some trigonomic techniques that I think I remember, but they're coming into play, and I just feel like this is a good chance to strengthen those pieces. So what is inverse? Okay. So I might just hang on while those download. How long is this going to take? It says, yeah, it says it's only going to be about a minute. So I'm just going to get a little bit of water, and then I will come back here while this is downloading, and I will start. So Rasmus is asking, why am I using paper flashcards? A couple reasons. One, there's not much time. Like I'm only looking at like a week's period, so SRS isn't going to really help that much. SRS is if you want to remember things over like months or years. The second benefit for SRS is if you're doing tons of flashcards. So obviously, if you're doing 1,000 flashcards, paper is going to be super tedious to practice that. I don't think I'm going to have more than 20. So I'm just doing this because it just is easier. Sometimes writing it down, like the other thing too is that like I'm dealing things that have like formulas. Maybe I just can do it like here. Like these have like formulas with like square roots and stuff. Doing that in Anki means I have to code it in LaTeX, which is always kind of tedious. It's just easier to do this. So if I had to do like 100 of these and I was doing it over a couple months, then I would probably do SRS. I would just take a picture of the thing that I wrote down and put them in the flashcards. I generally prefer spaced repetition systems, but they're more of a long-term thing, whereas this is just, I want to memorize this enough so that it's not impeding me during the exam. But I don't really care about long-term retention of these particular factoids. Which may beg the question of why master them if I don't memorize them even for this here. And for me, as I said, one of one of the things when I'm studying is that I often try to pick some sort of benchmark that I like to reach. Now that benchmark is not always going to be perfectly aligned with what your initial intention was with the goal. But my initial intention, which was to get a better intuition for quantum mechanics, is too vague to be actionable at all. So I've reduced that to, can I pass this exam? Now, once I've got that idea of can I pass that exam and I'm working towards that benchmark, I can think about, well, where is that going to bias me towards doing things that I care about or don't care about? So for me, what I would really learn is some understanding of quantum mechanics. Why is it the way it is? Some kind of visual intuition. And I'm trying to do that by starting by trying to get comfortable with this mathematical structure. So these things are kind of necessary for this benchmark goal, but they're not super important, I don't think, for my long-term goal. So how are we doing for download? It looks like I'm done. Okay, so I'm just gonna grab some water and then I'm gonna pop in the next video and switch over. And I am gonna make more flashcards. I only made, like, how many do I have here? 7. I only have 7 flashcards here, so I don't have a lot of flashcards. And part of the reason I don't have a lot of flashcards is just because I don't want a lot of flashcards. I don't want to be just doing tons and tons of flashcards. But at the same time, I'm going to, when I work through problem sets and do stuff, if there's facts, I should have been doing this in the beginning of the class. I haven't used it in physics classes a lot, so I didn't think it would be that important. But going through the problem sets, I'm now recognizing that there are some questions that are of that nature. I don't know how relevant they're going to be on the exam, so I don't think I'm going to have more than 2 dozen, let's say. All right. Okay, let me open the video here. I think let's start with the dispersive medium. How long is this video? Okay. So this is going to be a full lecture, so I'm just going to write down the lecture instead of doing a Feynman technique because I've never watched this one before. So because I've never seen this lecture before, I figure it's probably going to be, it's kind of hard to know whether to adjust this, kind of blocking it out here. You know what, I might, yeah, I might just, I'll just keep this over here. It's kind of hard to fit everything in. All right, so I've never watched this lecture before, so this is going to be, this is lecture 13. So why did I pick this one to do? Because one of the questions involved this WK of dispersive media, and it also was about phase and group velocity. This has been coming up in the class. I could go through all of 803, but I felt like that was probably not going to be most helpful because it's only select concepts that are going to apply, and a lot of them I've already practiced.
Put it under a Creative Commons license. Your support. Continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Hello, everybody. Welcome back to 803. Today, we are going to continue the discussion of waves. That's a very interesting phenomenon today, which is dispersion. And before that, we will discuss a bit, just to give you some reminder about what we have learned so far. So we discovered this wave equation.
Let's write down this wave equation. So this is the same idea of the Schrodinger equation we have. So the second time derivative is related to the second spatial derivative. Acceleration. So I think this is velocity squared. I think that's what that is. Times spatial curvature.
Which is shown here in the class. And we also show you that it describes 3 different kinds of systems, which we included in the lecture. The massive strings, which the string can actually oscillate up in that direction. And also we discussed about sound waves, right? This is also discussed in the previous lecture. And sound waves can be described by wave equation. And finally, last time we discussed electromagnetic waves. It's a special kind of waves involving 2 oscillating fields. One is actually the electric field, the other one is magnetic field, right? So that's kind of interesting because this is actually slightly different from what we discussed before in the previous 2 cases. This is actually a 3-dimensional wave, and also involving 2 different components. And we also discussed the solution, the traveling wave solution of the electromagnetic waves. As you can see from here, the electric field is shown as the red, and the magnetic field is shown as the blue. And you can see that in case of traveling wave, they are in phase, and the magnitude reach maxima simultaneously for the electric field and the magnetic field. And while in the case of standing wave, there's a phase difference, right? So
this is actually kind of interesting. I'm going to write this down. So this one is going to be oh man, I can't draw shit.
they don't reach maxima simultaneously in the standing electromagnetic field case. Okay. So what are we going to discuss today? We would like to discuss the strategy to send information using waves. Okay. How do we actually send information using waves? So you can say, okay, we just do. Maybe I can just send a harmonic oscillation, right? So if I do this harmonic oscillation, and I can actually produce harmonic waves. They are moving up and down, and it's actually with a constant angular momentum and angular frequency. And maybe that's a way to send the information. But this kind of wave is not, in reality, not super helpful, because if you fill the whole space with harmonic waves, then you don't know when did you actually send the signal, right? Because it's always oscillating up and down, so you don't know the starting time of the signal, right? So in reality, this kind of simple harmonic oscillating traveling wave is not super helpful. So what is actually helpful? That's the question. So what is actually helpful is to produce square pulse, for example. Right? We can create square pulse. For example, in this case, I can create a square pulse here, and in the next time interval, I don't create a square pulse. In the next time interval, I don't do anything, and I create another square pulse here, etc. Okay. If you use this kind of strategy, what we can do is to have some kind of receiver here to actually measure the magnitude of the pulse, okay? And then we can actually interpret this data. So this way is going to work. The positive x direction will go to the right hand side of the board, and the receiver will be able to interpret this data by tracing the ratio on the energy or on the measured amplitude. Then we can say, oh, now I receive a 0, and the next signal I receive is 1, and this one is 0, and 0, and 1, and 0. In this way, I can actually send information, and this information can be verified at the function of time. Okay. So in short, what will be useful is probably to use a narrow square pulse, and that would be very helpful in transmitting information. Okay. So if we consider an ideal string case, okay, if I have an ideal string, as we learned before, the behavior of this string is described by the wave equation, like partial square psi, partial t square, and this is equal to b square, partial square psi, partial t square. Okay, and this b is actually related to the speed of the progressing wave, right? As we discussed before, the progressing wave solution. Okay, and if I have this idealized string and a simple version of my equation, then I will be able to derive the dispersion relation, right? So I can now write out my harmonic progressing wave in the form of sine kx minus omega t. I have a harmonic oscillating wave propagating toward the positive x direction at speed of b. Okay, I can write it down in this functional form where k is a reminder, is a wave number, and the omega is actually describing how is actually the angular frequency. And therefore, if I plug in this solution, and of course I can have arbitrary amplitude. If I plug in this solution to this equation, then what I'm going to get is, as we did in the last few lectures, there will be a fixed relation between k, which is the wave number, and omega, the angular frequency. So the fixed relation is actually omega over k will be equal to v, which is actually the velocity in this.
Okay, hold on a sec. This is kind of important. This is not related to velocity. You still have to know the characteristic velocity on it. I was thinking that I might be able to.
Wave equation, and from the previous discussion, we know this is actually equal to the square root of t over rho L, where t is actually the tension, the constant tension which we apply on the string, and it's actually the mass rapidity as we might. Okay. So what does this mean? What does this equation mean? We call it dispersion relation at that time, right? But we actually didn't explain why do that, right? So we are going to learn why this is called dispersion relation. Omega is a function of k. And in this case, in this very simplified, idealized case, omega over k is ratio. Okay, we know this is related to the propagation of the speed. The propagation of the harmonic wave, okay, is equal to v. V is a constant, right? It's independent of k. This ratio is independent of k. What does that mean? That means if I prepare waves, okay, with different wave number, or in the other words, waves with different wavelengths, they are going to propagate at the same speed, right? So the speed of the harmonic progressing wave is independent of the wavelengths, okay? That's actually very good because in this case, if I prepare the square pulse, okay, as we learned before, this square pulse is actually a very complicated object, right? Square pulse is really very complicated. You can do a Fourier decomposition, right, as we did before, and we need infinite number of turns of harmonic oscillating waves. We should add them together so that I can produce a square pulse, okay? And as I mentioned here, if the dispersion relation is omega over k is a constant, that means all the whatever wavelength pulse, which actually added together and produce this square pulse, going to be happening at the same speed. Therefore, if I have this square pulse in the beginning, at some time t, what I'm going to get is that, okay, this is the original position of the square pulse, and after some time t, the square pulse will move by v times t in the horizontal direction, and the shape of the pulse is not going to be changed. Okay, because no matter what kind of wavelength which produces square pulse, all the components in the square pulse are propagating at the same speed. Okay, So this kind of system, which actually satisfies this kind of dispersion relation is called non-dispersive medium, right? No dispersion was happening in this case, in this highly idealized case. Okay. We also know that in case of the string, we are actually making it too idealized, right? So if we consider a more realistic string, then I have to consider an important phenomenon, which is important property of the string. For example, stiffness, right? What do I mean by stiffness? So, for example, if I take a string from piano string, okay, even if I don't apply any tension to the string, okay, if I bend the string, even light, right, it's going to bounce back and restore to its original shape, right? So that's actually what I call stiffness. It's a different contribution compared to the string tension, right? So what we have been discussing so far, that this restoring force is actually coming from the string tension T, okay? What will happen if I introduce additional contribution from the stiffness? Okay, this stiffness is actually completely related to the string tension, and it also wants to restore the shape of the string, okay? Before we go to the modeling, I would like to take some vote to predict what is going to happen. How many of you will predict that if I include the stiffness of the string, okay, into my equation, will the speed of propagation increase? How many of you think what is going to happen? 1, 2, 3, 4, 5. Okay. So some of you predict the speed of propagation will increase. How many of you predict that the speed of propagation of the harmonic wave will stay the same? How many of you? 1. Okay, 1. Okay, how many of you actually predict that the speed of propagation will decrease? Okay, so all the other students don't have T. Okay, want to wait for the answer. All right, so you can see that it is actually not completely obvious before we solve this question, and we are going to solve it with a simple model which actually slightly modify the idealized case, the idealized equation. Okay, so now one semi-realistic model which I can introduce is to add additional term to the wave equation. So I can now rewrite my wave equation to improve this effect to describe a realistic string, and now this is r squared psi times t squared. This will be equal to b squared r squared psi times t squared. And the additional term which I put into this again is minus alpha up to the 4 psi r x. And this is actually the contribution which from stiffness. Okay. So you can see that the wave equation is now modified, and what I could do in order to get the relation between omega and the k, what I could do is that I can now start with this harmonic wave solution, policy wave solution, plug that into this equation, this modified equation, and see what will happen. Okay, if I plug this equation into that modified wave equation, what I'm going to get is the following. So basically, the left hand side I'm going to get omega squared, okay, minus omega squared, and the right hand side you get b squared minus k squared, and plus alpha k to the 4 in the right hand side. Okay, so of course I can now cancel this minus sign. This will become plus, and this will become minus. And you can see that the relation between omega and the k is now different. Okay, after I introduce this term, which is proportional to alpha. Alpha is actually describing how stiff this string is. Okay, of course now I can calculate omega over k, which is
the nice thing about these lectures is that you don't have to write down everything. You can pause it and like, oh, that was important. I should have written that down. Go back. So it should be x squared, right? Yeah.
actually, as we mentioned before, right? It is the speed of the propagation of a harmonic wave. Okay, so basically, if I calculate omega over k from this equation, then basically what you get is v square root of 1 plus alpha k squared. Okay, so if you look at this equation, okay, the first reaction is, oh, now this omega and k ratio is not a constant anymore, but a function of k. What does that mean? That means if I prepare progressing waves with different wavelengths or wave number k, okay, it's going to be propagating at different speed. Okay, before we introduce this into the model, the ratio omega and k is a constant independent of k. Now, once you introduce this model into the equation and you plug in the progressing wave solution to actually check the dispersion relation obtained from this equation, you find that the progressing wave, the speed of progressing wave depends on how distorted this progressing wave is. Okay, so now we compare these two situations in this graph, omega versus k. Okay, so we will see this dispersion relation graph very often in the class today. The y-axis is actually the omega, the angular frequency, and the k is the wave number, 2 pi over lambda. Okay, in the original case, I have this idealized string, obey the wave equation which I will introduce in the previous lectures. If I plot omega as a function of k, what I get is a straight line. Okay. This one, right? Oh, maybe I made some mistake here. So it should be also plus here, right? 1, 2. No. So you have this omega. Okay, so this is omega squared, and actually you have this minus sign here, right? So this should be minus. Right, and this should be okay. Let's go back to the original equation. Okay, so basically you get so if I copy this equation to this equation, right? So basically I get minus omega squared out of it, and I get minus k squared out of this, right? And I'm going to get plus k to the 4 out of this r squared to the 4 sine r to x to the 4, right? Okay, therefore this should be minus. Okay, we can make this. Thank you very much for that. Oh yeah, I'm sorry. Not my mistake today. Yeah, what did I do? Okay, I must be drunk today. Thank you very much. Any more mistake? Okay, fortunately not, right? Okay, very good. So let me do this again. So now I can modify my wave equation, right? Originally, the wave equation is partial square sine partial d squared equal to b squared partial square sine partial x squared. And now I add additional term, which is actually proportional to the partial square 4 sine partial x to the 4. Okay, if I add this term into again, and now I plug in the wave equation, the progressive wave solution into this equation, then I will get this formula. Okay, so now everything should be correct, and I have clear evidence that everybody's solid, so that's very good. And now I can cancel all the minus sign, right? And this become plus. And now we can actually calculate what will be the speed of propagation for this specific harmonic progressive wave, and omega over k will be equal to v squared to the 1 plus alpha k squared. Okay. Thank you very much for the contribution. And now we see that clearly this ratio depends on k, right? So if I plot this on top of the previous curve, which is actually obtained from here, okay, then what I'm going to get is something like this. In the beginning, it's very close to the non-dispersive case, and it goes up because of this alpha contribution. Alpha is actually a positive number in my model, and the k is actually the wave number. Okay, so what is going to happen is that basically after you improve the stiffness, the slope of this curve is changing as a function of k. Okay. What do I learn from this exercise is that if I increase k, okay, if I have a very large k, okay, that means I have a very small lambda, right? Because k is actually 2 pi over lambda. Okay, so that means I'm looking at something really distorted like this. Okay, both string tension and the stiffness wants to restore the string back to normal. Therefore, what is happening is that you are going to get additional restoring force, right? Therefore, as we actually calculated here, if alpha is actually positive, then the velocity actually increased, which is to what actually what we actually get before we actually add this into alpha. Okay, so I think that makes sense, right? Because the stiffness also wants to restore the distortion. Therefore, you have larger restoring force. Therefore, the speed of propagation of this harmonic wave will increase. Okay, so that's pretty nice. But what does that mean to our project? Okay, our project is to send information from one place to the other place, right? So what we just discussed is that we can actually send a square pulse and not propagate. Okay, a square pulse can be decomposed into many pieces, many harmonic waves. Okay, before the square pulse works because all the waves with different wavelengths are actually moving at this constant speed, right? Independent of wavelengths. Now we are in trouble, right? As you can see here, that now the speed, which is omega over k, depends on the wave number or wavelengths. Therefore, different components which actually are needed to create a square pulse are going to be propagating at different speed. You can say, oh, this is actually mathematics, so I don't believe you. A square pulse is a square pulse, and that's mathematics, that's math department. But we can actually really see that in the experiment. Okay, so take a look at this demonstration. Maybe you didn't notice that before, but we have seen this effect from the previous lectures. Okay, so I can now create a square, not really a square pulse, but actually some kind of pulse. Okay, I can create some kind of pulse like this. Okay, and as we learned before, right, when this pulse has through an open end, it's going to be bounced back, right? So therefore, I can have a limit. Okay, I can actually show you this demo in a limited setup, but this pulse is going to be going back and forth, right? Because I have open end, okay, as we discussed before. Okay, what is going to happen is that since we have a realistic system, what is going to happen is that this pulse will become wider and wider. Right? That's the prediction coming from this equation. Right? Different component with different wavelengths is going to be propagating at different speed. Therefore, this pulse is going to become lighter, and we can see that. Okay, so let me quickly produce a pulse and see what happens. Okay, originally it's actually really sharp, and you can see that really the width of the pulse become wider and wider, and at some point it disappears. Okay, if I have a very long setup, what we are going to see is that it's going to be propagating toward the same direction, and the width of the pulse is actually going to be increasing as a function of time. Let's take a look at this again. Now this time we have a negative pulse. You sort of see very similar thing. And also you can see that there's some strange vibration actually lag behind the main pulse, right? So that means different, harmonic waves with different wavelengths really are propagating at different speed. And for that, to demonstrate this effect, I also prepared some demonstration, which actually are based on our calculation. Okay, so you can say that, okay, now I can see the dispersion in the experiment. How do I get this calculation actually match with experimental data? Right? How do we really run a simulation and see what happens? Okay, so what this example should do is in the beginning, okay, it will do integration like crazy. Okay, in order to get all the components calculated, then it's going to propagate all those paths, all those different paths with this component through the beginning. Okay, and there will be two different colors. One is actually blue, which is the original shape. The other one is actually the one with steepness turned up. Okay, so now in the beginning, I can set the alpha value to be 0.02 and see what happens, and I will produce triangular pulse. Okay, you can see that now the program is really working very hard to calculate all the components. Okay, from 1 to 199 and equal to 1 to 199. And now this individual components are propagating through the median. And you can see that originally the shape is like the blue shape, a triangular shape. And you can see that as a function of time, the pulse become wider and wider. Okay. Now, of course, I can increase the alpha to 0.02 and see what happens. Remember, from 0.02 to 0.2 and see what happens. Usually expect a much larger dispersion. And you can see that now in the beginning, it's doing the integration. And you can see that this time, because the alpha is actually larger, therefore you see that this effect is actually this broadening is actually happening earlier, and then it becomes broader and broader. And there are a lot of strange structures that you can see also from the demo are produced because different components are actually propagating at different speed. Okay, so of course we have NIT. So in this course we have NIT waves, right? So let's take a look at the NIT wave and see what happens. Now you see that they are very sharp edge, which actually require really a lot of effort to reproduce that. You can see that NIT is kind of distorted as a function of time. It's kind of still identified peak, but it's actually now displaced. And in the end of the simulation, you cannot see even recognize that actually originally an NIT signal which you sent from the source. Okay. So what I want to say is that this effect, this dispersion effect, is really an enemy, which is actually very dangerous, and now it actually will prevent us from sending high quality signals. Right. Okay. Any questions about those demos? Yes. Yeah. So this is because the stiffness is actually symmetric, right? So if you bend this thing, if you bend the string, then there are contribution from positive and negative part. Okay. If you have a partial to the 3, partial to the x to 3 component, then it's going to be symmetric, and this actually depends on what physics teach. And also in this modeling, we also match with our experimental data very well. Okay. Very good question. And on the other hand, without considering the stiffness, okay, you can also go back to the infinite number of coupled oscillator case. If you instead take an example which is actually not super small displacement approximation, you take the next leading order term, then you see that the partial to the 3, partial x to the 3 term actually cancel because it's symmetric, that's what I argued. And you will be able to also obtain this term when you have slightly larger displacement with respect to the equilibrium position. Okay, so I hope that answers your question. Any other question? Yes. So that when you pass through the median. Yeah, and the amount you change the speed of different wavelengths actually different, right? Very good question. Okay, so very good. We have good questions, and we can see that if I now turn on the alpha and make the alpha value large, then we can see that the information is distorted. Okay, and this involves infinite number of terms. And then in this case, in this new demo, which I show here, I have alpha value equals 0.2. Therefore, the effect of dispersion is actually much larger than what we showed before. And then you can see that this NIT wave quickly become something like Gaussian wave. Right? Okay. Okay, so very good. So you can say, okay, you are making an example, which maybe it's very interesting example, but it involves too many terms, right? You have infinite number of progressing waves in this example. Okay, it's very difficult to understand, right? How about we go back to a much simpler example? Okay, what we can do is that instead of going through infinite number of harmonic waves, now we just consider 2 waves and overlap these 2 waves together and see what happens. Okay, and then see what we can learn from it, because the required number of harmonic waves to describe such a path is too complicated. Right? So you can say that, okay, now let's just consider 2 waves and see what we can learn from this. And this is exactly what I'm going to do now. So from Bolek's lecture, I hope he covered the beat phenomenon. Right? So basically, what is the beat phenomenon? Beat phenomenon happens when you overlap 2 waves, 2 harmonic waves. They have pretty close wavelengths, okay, but not the same. Okay, and now if you add 2 waves together, that's actually what we're going to get. We're going to get something which is oscillating really, really fast, which is actually called the carrier. Okay, and also you can see that the magnitude of the oscillation is actually changing the function of position, and that we call it envelope. Okay, so that is a big phenomenon which we learned from previous lectures. So in this example, I'm going to add 2 waves together. So the first wave is described by side. Okay, it's denoted by side 1. It's function S and P, and it has a function form A is the amplitude, and the sign K1x minus omega t. Omega 1t. Okay, this is actually a progressing wave propagating toward the right-hand side of the board, the positive direction of the x-axis in my coordinate system, and it has a wave number K1 and angular frequency omega 1. Okay, and I can also write down my second wave, which I would like to overlap with the first wave. Right, so this is actually having exactly the same amplitude, which is A, and it is described by some function, and you have wave number K2 x minus omega 2t, angular frequency omega 2. Okay, with these 2 equations, we can calculate the speed of propagation for the individual waves, right? So the first one, I can calculate the speed of propagation v1 will be equal to omega 1 over k1. Very similarly, we can also calculate the speed of propagation for the second wave, which is omega 2 over k2. Okay? So now what I'm going to do is to calculate the sum of these two waves. So I have the total diffusion psi is equal to psi 1 plus psi 2. Okay? So what I'm going to do is to overlap these two waves and see what happens. And for that, I need this formula, which is sine A plus sine B. And this will be equal to 2 times sine A plus B over 2 and sine, cosine A minus B. Okay? So if I use that formula, okay, basically what I'm going to get is we have 2 times from that formula, so we have 2a, okay, sine k1 plus k2 over 2x minus omega 1 plus omega 2 over 2t. Right? So basically the first term is a sine function, and the content is actually a plus b. Therefore, you add these two together, divided by 2, and basically this is actually what? About 10. Okay. The second term is a cosine term. You get cosine here, but now you calculate a minus b, which is this term minus that term, divided by 2. Then basically what you get is k1 minus k2 divided by 2 times x minus omega 1 minus omega 2 over 2t. Okay, so that is actually what will happen if you add these two waves together. Okay, until now everything is exact, and I would like to add additional conditions or additional assumptions when I discuss this solution. Okay, so how about in order to produce a big phenomena, I need to make the wavelengths very similar between the two waves, right? So therefore, what I'm going to do is that I'm going to assume k1 is very close to k2, is roughly k. Okay, and because of this, since I have a continuous function, if k1 is really close to k2, that means omega 1 is going to be also very close to omega 2, right? So what I'm going to get is omega 1 is going to be also very similar to omega 2, and I will call it omega. Okay? So if I do this, when I have very similar k1 and k2, what is going to happen? What is going to happen is that k1 minus k2 will be very small, right? So that means this very small k means large wavelengths, right? Therefore, this cosine term will become the envelope. Right? Because it's actually a slowly varying amplitude as a function of position, because the k is very small, k small means lambda large. Therefore, the amplitude is going to be having this modulation, which is actually like an envelope. The speed of this envelope, the oscillation of this envelope is actually controlled by the k. Okay. Let's look at the left hand side. K1 plus K2 over 2. It's kind of like calculating the average of the first and second of the wave number of the first and second wave, right? So if you calculate the average, it can be still very large. Therefore, you have small lambda, right, compared to the difference, right? Therefore, you see that actually contribute to those little structures in this reference called carrier. Yes. Yeah, so they can be different, right? Yeah, so you also divide, right? So you can produce something like a carrier, even when k1 is not equal to k2, right? It's just an average, right? Yeah. But then on the other hand, the difference k1 and k2 will be also large. Therefore, it's not as easy as what we have been doing here to identify who is the carrier and who is the envelope. Okay, so you do get some kind of graph which is oscillating really fast, but the envelope is going to be also oscillating really fast. It's harder to see all the structure, but you have to do like this. Very good question. So now I have this set up. I assume that they are very close to each other. So now I can define phase velocity. Finally, we define what is actually the phase velocity. The phase velocity, I call it Vp. You can see that before I already have been using phase velocity Vp for the previous discussions, right? In the case of dispersive medium, the phase velocity is as a Vp, which is the velocity in the equation, right? And in this case, Vp will be equal to omega over k, as we discussed before. That's actually the definition of this phase velocity. Okay, and I can now also define the group velocity. Okay, the group velocity is actually the velocity of the envelope. Okay, I can calculate the velocity of the envelope. Right? In the case of phase velocity, I'm calculating the velocity of the carrier. Right? Okay, I'm taking a ratio of the average, and actually the average is so close to k and omega. Therefore, the phase velocity Vp will give us the speed of the propagation of the carrier, which is actually omega over k. I call it Vp. And in case of group velocity, I call it Vg. Okay, Vg is describing the speed of propagation of the envelope. Therefore, what I'm getting is omega 1 minus omega 2. Okay, divided by k1 minus k2. Also, then have a factor. Two length, which is actually cancelled. Okay, and when they are really so close to each other, this is actually roughly like d omega dk. Any questions so far? So we have two different kinds of speed. One is actually related to the phase velocity, which is one is actually called phase velocity, is related to the speed of the carrier. Okay, the other one is provable line.
Let me write this down here. I gotta sharpen my pencils again. We have which is actually related to the speed of the envelope. Okay, so let me describe you a few interesting examples and see what we can actually learn from this. In the first example, I'm working on a non-dispersive medium. Okay, if I have a non-dispersive medium, okay, then basically what I'm going to get is that omega will be proportional to k. If I plot omega versus k, it's a straight line. Okay, now if I have omega, I choose the omega of the two, omega 1 and omega 2. Of the two waves to be roughly equal to omega 0. Okay, I can now evaluate the VP. The VP will be the slope, right, of this point, on the slope of a line connecting the 0 to that point, right, which is actually omega over k, right? So that's actually the definition of the phase velocity. I will get this slope. This is the slope of this line is actually called is related to the phase velocity. I can also calculate the slope of a line cut through this point, but actually cut through this curve. And then in this case, I'm also going to get a line overlapping with phase velocity, because in this case, omega over k is a constant, which is v. Therefore, if no matter what you calculate, if you calculate Vp as a ratio of omega and k, or you calculate Vg, which is actually the slope of the line cutting through that point, you always get actually v. Okay, therefore, what we learn from here is that for a non-dispersive medium, Vp will be equal to Vg. Okay, that means
both of these two curves, both of the curve of envelope, describing the envelope and describing the carrier, is going to be propagating at the same speed. Okay, any questions? So the whole thing is going to be moving at a constant speed. For that, I can now show you some code we have prepared, some simulation we have prepared. Okay, see. So what it does is that it really, oh, a second, this is maybe 0. Okay, so this is the case when I have a non-dispersive medium. Okay, if I have a non-dispersive medium, what is going to happen is that both the carrier, which is the speed of the auto-stable structure, and the envelope is going to be propagating at the same speed. So you can see that now it's like a fixed pattern. It's propagating toward the right-hand side, and the relative motion between the defined structure and the envelope is actually 0. So basically, you have exactly the same pattern as a function of time. Okay, so now I'm going to move away from the non-dispersive medium. How about we discuss what will happen if we have consider the stiffness of the string and see what we get from there. So if I plot omega as a function of k, okay, and consider alpha to be non-zero, is a positive value. So if I have alpha to be a positive value, non-zero, okay, in this case, I'm going to get a curve like this. Okay, the slope is actually changing, and because it's curving down, it is curving up, because if you have k large, then you see that the ratio of omega and k actually increase. Okay, so that is actually the kind of curve which we will get if I set the omega of the first and second wave of increase in this study to be omega 0. And basically, what we are going to get is that, okay, now I have this point here on the curve. Okay, if I calculate the phase velocity, the phase velocity, how do I calculate that? I can now connect 0 and that point by line. Okay, and I can now calculate the slope of this line, and I can get the phase velocity with p. Okay. On the other hand, I can also calculate the slope of a line passing through tangential to the point of interest. Okay, and that is going to give me the group velocity. Okay, as you can see from here, which slope is actually larger? Anybody know? Group velocity is larger, right? So in this case, if I turn down alpha greater than 0, what is going to happen is that since the group velocity is larger than the phase velocity, that means if I go back to that picture, okay, the envelope is going to be moving faster than the fine structure inside the envelope. How about we take a 5-minute break from here and we continue the discussion after the break? We should continue the break. Welcome back, everybody. So we will continue the discussion of the phenomena. So what we have shown you is that based on those curves, actually we can actually determine what will be the relative velocity of the what will be the velocity of the carrier, which is actually denoted by et, and what will be the velocity of the envelope, which is actually denoted by the group velocity. Okay. And in this case, what I'm actually plotting here is that in this case, because alpha is actually greater than 0, therefore this curve is actually curving up. Therefore, you have larger group velocity compared to the phase velocity. So what you would expect is that the envelope is going to be actually progressing at the speed higher than the speed of the carrier. Okay. On the other hand, if magically, okay, I can construct some kind of a median which can be described in this situation alpha smaller than 0, what is going to happen? So if I plot that, if I plot the situation with alpha smaller than 0, so and now I plot omega as a function of k, what is going to happen is like this. So basically, you have something which is actually curving down. Okay. So if I now again work on some point of interest here, okay, you can see that the slope of the phase velocity is now actually the slope of the phase velocity is now actually larger than the slope which is actually from the line cutting through the tangential to the curve, which is actually getting you the group velocity. So in the case of alpha smaller than 0, which is some strange medium which I can create from whatever plasma or some really strange kind of material of interest, if that happens, then that means your group velocity will be smaller than the phase velocity. Okay, and if you look at this point here, you can see that this curve actually reach a maxima here, and if you actually are operating at this point, what is going to happen? What is going to happen is that if you calculate the group velocity, what will be the value? It will be 0. What does that mean? That means the envelope will not be moving at all. Okay, but the carriers are still moving. Okay, so at this point, you are then going to get group velocity equal to 0. Okay, and finally, if you actually going to a very large k value in this scenario, alpha smaller than 0, you see that even you can have phase velocity will be positive, because it's actually a positive slope, and the group velocity actually is negative. Right? What does that mean? That means you are going to see a situation that the carriers are progressing in a positive direction, and the envelope is going to be progressing in the negative direction. focusing to the left-hand side of the book. So what does that mean? That means this wave is doing what Michael Jackson is doing, right? It's actually doing, right? So this is actually the kind of thing which could happen. That it looks like that you are doing, you're going forward, because all the carriers are moving in the positive direction, but the body is actually going toward a negative direction. Okay, maybe I can also the move work at some point. Okay, so let's go back to the demonstration which I got started and somehow I got messed up. So let's take a look at the demo again. So let's look at all the different situations at once. So in this case, as we discussed before, this is actually happening in the non-dispersive situation. Right? In this situation, you have a straight line, non-dispersive medium actually give you always the group velocity equal to phase velocity. Okay, so that means the carrier and the envelope is going to be moving in the same direction at the same speed. Okay. On the other hand, in this case, we can actually have a situation that the phase velocity is actually faster than the group velocity. Okay, so what I mean is actually the situation here. The phase velocity calculated from a line connected from 0 to that point, okay, is actually having a larger slope compared to the tangential line. And you will see this situation. So basically, you see that inside the envelope, all those carriers are actually moving faster than the envelope. Now, I can have a dispersive medium where the group velocity is equal to 0. So what is going to happen is that really the envelope is actually not moving. It's not like this, right? But the body is not moving, right? So you have some carriers inside this in this structure is actually moving forward, but the envelope is actually not moving. Okay. So finally, the last situation is really interesting. So that means in this situation, this is actually having the group velocity equal. The group velocity is actually having different sign compared to the phase velocity. So you can see that the whole structure of the envelope is actually moving backward, but the carrier is actually moving in the positive direction. In this example. Okay, so this is actually what we have learned from this deep phenomena, and we have covered the idea of phase velocity and the group velocity. So how about bounded system? How do we understand when we have a bounded system, and how does that evolve as a function of time? So if I have a system of two walls and one string, and of course I give you the tensor probability length and the string tension, and also the alpha, which is actually telling you about the steepness of this system. Okay. Again, I can write down psi st to be the sum of all the normal mole from 1 to infinity. Km sine kmx plus alpha m sine omega md plus beta. And then what we can do is that we can first get the initial conditions of this system and also the boundary conditions of this system. Then we actually just follow exactly the same procedure to obtain all the unknown coefficients. Then we will be able to evolve this system as a function of time, as I have demonstrated you in the beginning of the lecture. Right? So in this case, you can have two boundary conditions. One is actually at x equal to 0, and the other one is actually at x equal to L. Okay? In those boundaries, as we actually learned before, because the endpoints are fixed on the wall, therefore psi of 0 at the time t will be always equal to 0 for the left-hand side boundary condition. And very similarly, what we discussed before, psi of LP will be equal to 0 if you look at the right-hand side of the move, okay, of the system. Okay, so I don't want to repeat this because this is actually exactly the same calculation which we have done before, right? So with these two boundary conditions, we can actually conclude that Kn will be equal to n pi over L.
Yeah, I'm going to pause it here. I think I've gotten what I wanted to get out of this lecture. I'm going to switch over now. I think this was basically what I understood from the phase and group velocity, but it's good to see the kind of dispersive media as this sort of the angular frequency as a function of k. All right, now let me go and look now at so these ones here, I'm going to do a little differently because maybe I'll switch over here first. So these ones I'm going to do a little differently because they are things that I already know how to do. So that one was a little different because I had not actually ever taken a class on that, never learned it through a class. So I wanted to just watch. I figured that I kind of knew what it was about. I just wanted to get kind of some confirmation. And it was good to get a sense of what the wave dispersal formula is. Now I'm going to work on some things again from my list here. I think I want to work on which ones do I have here? I have integrating by parts, inverse substitution, trig identities. So what I'm going to do is I'll start with the integrating by parts. I'll write down what I understand it to be. Then I'll watch the lecture and make updates because I think this is something that I want to try to do a little bit of active recall on first. I think I remember the formula, but I will try my best to try to think through why it is that way, and then I'll watch the lectures. sometimes it's helpful to do this. I'm not going to go too far on that beyond just writing down the formula, but I will try to do a blind Feynman technique without actually looking at the thing, and then I'll watch the video. I might not watch the whole video. I might just watch part of it. Just depends on how much we're doing. So I'm just going to sharpen my pencils because they're all really dull right now. All right. So let me just start. I'll put this over here for right now. This is minus. Is that it? I think they're maybe reversed. Let me just look up the formula real quick here. Dx. Ah, right. X minus. Okay. Go back here. So I'm pretty sure this should be. I do this wrong. Sine is going to go back. This is going to go cosine. And this is minus cosine x. All right, let's try it on a Gaussian here. Rasmus is asking, do you have any tips for staying concentrated when listening to tough lectures like you're doing right now? Take more notes. I wasn't taking that much notes in that last one because I kind of understood it. But if you're listening to a tough lecture or seminar, take more notes. There's a kind of two things at play there. One of them is if your working memory is overloaded so that you don't understand what's happening, what's going through, then it's going to be a lot harder. So if you really can't understand what's going on, I try to jot as much down as I can, and then you can go back over it later. Whereas the other thing is about concentrating, of just staying focused, of just maintaining your attention. And so for that one, taking notes helps as well. So I usually, if I'm really not understanding, like I'm doing videos right now, so I would pause more if I didn't understand something. All right, let's try another one here. So we have squared over, I think this is so trying this, we have what? What is the integration for the Gaussian? No elementary indefinite integral. So I'm just going to call this x squared. So this one I don't understand, because this is going to be, maybe this is not the right way to do it. Let's go try to do it the other way around. E to the x squared is what? F of g of x on the df x df dg g dx f is equal to e dx g is equal to x squared the FTG is going to be minus times x is going to be minus oops, that's e to the x. So it's going to be I guess these are just going to cancel, right? It's going to be, oh, e to the x times this. So I have minus it could be plus, and this is a minus. So is equal to they just keep going up forever, though, don't they? Or do I want to do it the other way? Yeah, I think it has to be done the other way. So already integrating the parts. Let's try it again. also pi x. Get this equal to so we get root pi times is that right? No. No. So n e to the minus I want to integrate. We're going to drop a factor of what, -2. I think that's what I... -2. Oh no, n -2. N -2, because there's no x here now. And then this should be not -2n. No. It should be divided by -2. Okay, I think I understand integrating by parts, but I would like, is there a more visual intuition of why this is the case? Let's thank you. I appreciate that. I think I'm in need of a new one, but I appreciate that. Let me jump over to where's my scene with the lecture? Here we go. So I'm going to just look at integrating by parts. I'm going to just do it quickly because I just want to see if there's some sort of visual intuition about this.
Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right. Now, to start out today, we're going to finish up what we did last time, which has to do with partial fractions. I told you how to do partial fractions in several special cases, and everybody was trying to figure out what the general picture was. But I'd like to lay that out. I'll still only do it for an example, but it will be somehow a bigger example. What is partial fractions? Remember, is a method for breaking up so-called rational functions, which are ratios of polynomials, and it shows you that you can always integrate them. That's really the theme here, and this is what's reassuring, is that it always works. That's really the bottom line, and that's good because there are a lot of integrals that don't have formulas, and these do. It always works, but maybe with lots of help, so maybe slowly. There's a little bit of bad news, and I have to be totally honest and tell you what all the bad news is, along with the good news. The first step, which maybe I should be calling step 0, I had step 1, 2, and 3 last time, is long division. That's the step where you take your polynomial, divide by your other polynomial, and you find the quotient plus some remainder. And you do that by long division, and the quotient is easy to take the answer derivative of because it's just a polynomial. And the key extra property here is that the degree of the numerator now over here, this remainder, is strictly less than the degree of the denominator. So then you can do the next step. Now, the next step which I called step 1 last time. It's great imagination. It's right after step 0. Step 1 was to factor the denominator. And I'm going to illustrate by example what the step is here. I don't know, maybe we'll do this. Some polynomial here, maybe cube this one. All right, so here I factored the denominator.
I'm going to do this. Go over to where we have integrating by parts.
Parts. It's just the fundamental theorem of calculus, if you like, coupled with the product formula, sort of unbounded, read in reverse. And here's how that works. If you take the product of two functions and you differentiate them, then we know that the product rule says that this is u prime v plus uv prime. And now I'm just going to rearrange this in the following way. I'm going to solve for uv prime. That is this term here. So what is this term? It's this other term, uv, the quantity prime, minus the the other piece. All right, so I just rewrote this equation, and now I'm going to integrate it. So here's the formula. The integral of the left-hand side is equal to the integral of the right-hand side. Well, when I
Okay, so
integrate a derivative, I get back the function itself. That's the fundamental theorem. So this is it. Sorry, I missed the dx, which is important. I apologize. Let's put that in there. Okay, so this is the integration by parts formula. I'm going to write it one more time with the limits stuck in.
all right, that's good enough for this. Let's go to what do I want to do here? I'll just do Taylor series now, I guess. Taylor expansion. With what? With I think it's with polynomials. So I'm trying to see if I can recall exactly how the Taylor expansion works. So we have some I'll do it with pen for our function here. Let me just go over here to where's my Okay. I'm going to jump over and do the lecture quickly for this, like I did with the reading. I think I've got it, but I think it's always good to just get a little bit of a better picture. Wow, this is super bright. Let me just adjust this so it's not so washed out. Yeah, that's a bit better. All right. Now, where's my video?
The following content is provided under a Creative Commons license. The Open Courseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT Open Courseware at gaussian.mit.edu.
Last time, we left off with a question having to do with playing with blocks. This is supposed to give us a visceral feel for something, and we're having to do a series. And the question was whether I could stack these blocks, build a stack so that I'm going to try to, I'm already off balance here. The question is, can I build this so that the, let's draw a picture of it, so that the first block is like this, the next block is like this, and maybe the next block is like this. And notice there's no visible means of support for this block. It's completely to the left of the first block. And the question is, will this fall down? Or at least, or more precisely, eventually we'll ask, how far can we go? Now, before you answer this question, the claim is that this is a kind of a natural physical question which involves some important answer. No matter whether the answer is you can do it or you can't. So this is a good kind of math question where no matter what the answer is, when we figure out the answer, you're going to get something interesting out of it. Because there are two possibilities. Either there's a limit to how far to the left we can go, in which case it's a very interesting number. Or else there is no limit, you can go arbitrarily far, and that's also interesting and curious. And that's the difference between convergence and divergence, the thing we were talking about up to now concerning series. So my first question is, do you think that I can get it so that this thing doesn't fall down with well, at least I have about 8 blocks here or so. So you can vote now. How many in favor? I can succeed in doing this sort of thing with maybe more than 3 blocks. How many in favor? All right, somebody's voting twice. So that's good. I like that. How about opposed? So that was really close to a tie. All right, but I think that there's slightly more opposed. I don't know. You guys weren't that many, you could tell. Anyway, this was pretty close. All right, so now I'm going, because this is a real life thing, I'm going to try to do it. All right. All right. So now I'm going to tell you what the trick is. The trick is to do it backwards. When most people are playing with blocks, they decide to build it from the bottom up, right? But we're going to build it from the top down. And that's going to make it possible for us to do the optimal thing at each stage. So when I build it from the top down, the best I can do is, well, it'll fall off. I need to have it less, halfway across. That's the best I can do. So the top one I'm going to build like that. I'm going to take it as far to the left as I can. And then I'm going to put the next one down as far to the left as I can. And then the next one as far to the left as I can. Oh, that's a little too far. And then I'm going to do the next one as far to the left as I can. And I'm going to do the next one. Let's line it up first. As far to the left as I can. And the next one as far to the left as I can. All right, now, those of you who are in this line can... All right, let's see. All right, this is what it is. All right, so we can do that. All right, so now, the name for the... Well, we have these more than this one block, right? Obviously, I think... Now, I want you to think about what's going on here. The center of mass of the first block is this number. This new one, it's a length 2. And its center of mass is 1 further to the right than the center of mass that we had before. So in other words, I've added to this configuration n plus 1 more block, which is shifted, whose center of mass is not lined up with the center of mass of this, but actually over farther to the right. Right. So the new center of mass of this new block is this.
I'm just waiting to get to the point where he starts talking about Taylor series, Taylor expansion.
Now, I'm going to show you one reason why this is true, why the formula holds. And it's just the kind of manipulation that was done when these things were first introduced. And here's the idea of a proof. So suppose that this sum is equal to some number s, which is the sum of all of these numbers here. The first thing I'm going to do is I'm going to multiply by x. Okay, so if I multiply by x, let's think about that. I multiply by x on both the left and the right hand side. And on the left side, I get x plus x squared plus x cubed, and so forth. And on the right side, I get s times x. And now I'm going to subtract the two equations, one from the other. And there's a very, very substantial cancellation. This whole tail here gets canceled off, and the only thing that's left is 1. So when I subtract, I get 1 on the left-hand side. And on the right-hand side, I get s minus s times s. Right? And now that can be rewritten as s times 1 minus s. And so I've got my formula here. This is 1 over 1 minus s is equal to s. Right? Now, this reasoning has one flaw. It's not complete. And this reasoning is basically correct. It's incomplete because it requires that s exists. For example, it doesn't make any sense in the case x equals 1. So, for example, in the case x equals 1, we have 1 plus 1 plus 1 plus etc. equals whatever we call s. And when we multiply through by 1, we get 1 plus 1 plus 1 plus s times 1. And now you see that the subtraction gives us infinity minus infinity is equal to infinity minus infinity. That's what's really going on in the argument in this context. So it's just nonsense. I mean, it doesn't just make it meaningful. So this argument is great, and it gives us the right answer, but not always. And at times when it gives us the answer, the correct answer, is when the series is convergent. And that's why we care about convergence, because we want manipulations like this to be allowed. So the good case, this is the red case that we were describing last time. It's the evidence, but what we want is the good case, the convergent case. And that is the case when x is less than 1. So this is the convergent case. Okay, so there are much more detailed things to check exactly what's going on. I'm going to just say general words about how you recognize convergence. And you're not going to worry about so much about convergence because it works very, very well. And it's always easy to diagnose when there's convergence with power series. All right, so here's the general setup. The general setup is that we have not just coefficients 1 all the time, but any numbers. And we abbreviate that, which the summation notation is the sum a n s to the n, n equals 0 to infinity. And that's what's known as a power series. Fortunately, there's a very simple rule about how power series converge, and it's the following. There's a magic number r, which depends on these numbers here, such that, and this thing is known as radius of convergence. And the problem that we have is this number 1 here. This thing works for x less than 1. In our case, it's maybe x less than r, so that's on symmetric interval, right? That's the same as minus r less than x less than r. And this is a radius convergence. Okay, radius series converges. Converges. And then there's a region where every computation that you get will give you nonsense. So x greater than r is the sum a n x to the n diagrams. And x equals r is very delicate borderline and will not be used by x. Okay, we're going to stick inside the radius of convergence. Now the way you'll be able to recognize this is the following. What always happens is that these numbers tend to 0 exponentially fast for x in r, and doesn't even tend to 0 at all for x greater than r. Right? So it'll be totally obvious. When you look at this series here, what's happening when x less than r is that the numbers are getting smaller and smaller. When x is less than 1. When x is bigger, when the numbers are getting bigger and bigger, there's no chance that the series converges. So that's going to be the case with all power series. There's going to be a cutoff, and it'll be one particular number, and below that will be obviously convergence and computation. Above that, every formula will be wrong and won't make sense. So it's a very clean thing. There is this very subtle borderline, but we're not going to discuss that. This class is actually not used in direct studies of power series.
When the number is declining exponentially faster, it's just the number 1 over x.
Okay, so the question is, why was I able to tell you this one here? I was able to tell you not only is it going 0, but it's going exponentially fast. I'm telling you extra information. I'm telling you it always goes exponentially fast. You can identify it. In other words, you'll see it, and it will happen every single time. I'm just promising that it works that way. And it's really for the same reason that it works that way here. These are powers. And what's going on here is they're this close to powers, these ANs. All right? There's a long discussion of radius of convergence in many textbooks, but really it's not necessary, all right, for this purpose. Yeah. The question is how to find out. So I just said there's a long discussion of how to find radius of convergence in textbooks, but we will not be discussing that here. And it won't be necessary for you because it will be obvious in any given series what the arguments. It will always be either 1 or infinity. It will always work for all x, or maybe it will stop at some point, but it will be very clear where it stops, as it is for the geometric series. All right? Okay, so now I need to give you the basic facts and give you a few examples. So why are we looking at these series? The answer is we're looking at these series because the role that they play is exactly the reverse of this equation here. That is, and this is a theme which I try to emphasize throughout this course. You can read equalities in 2 directions. Both are interesting, typically. You can think, I don't know what the value of this is, here's a way to evaluate it, and there's the left side, the right side is a formula for the left side. Or you can think of the left side as being a formula for the right side. And the idea of series is that they're flexible enough to represent all the functions that we've encountered in this course. This is the tool which is very much like the decimal expansion, which allows you to represent numbers like square root of 2. Now we're going to be representing all the numbers, all the functions that we know, e to the x, arctangent, sine, cosine, all of those functions become completely flexible and completely available to us and computationally available to us directly. So that's what this is a tool for. It's just like decimal expansion is giving you a handle on all real numbers. So here's how it works. The rules for convergent power series are just like polynomials. All the manipulations operations that you do for power series are essentially the same as for polynomials. So what kinds of things do we do with polynomials? We add them, we multiply them together, we do substitutions. Right? We take one function of another function, we divide them. Okay? And these are all really not very surprising operations, and we'll be able to do them with power series too. The ones that are interesting and really interesting for calculus are the last two. We differentiate them, and we integrate them. And all of these operations we'll be able to do for power series as well. So now, let's explain the high points of this, which is mainly just the differentiation and the integration part. So if I take a series like this, and so forth, the formula for its derivative is just like polynomials. That's what I just said. Just like polynomials. So the derivative of the constant is 0. The derivative of this term is a1. This one is plus 2a2x. This one is 3a3x squared plus, etc. That's the formula. Similarly, if I integrate, well, there's an unknown constant you're going to put first rather than last, which corresponds to the a0 term, just going to get wiped out. That a0 term suddenly becomes a0x. And the antiderivative of this next term is a1x squared over 2. And the next term is a2x cubed over 3, and so forth. Yeah, question. Is this a series or a polynomial? Good question. It's a polynomial if it ends, if it goes on infinitely far, then it's a series. They look practically the same, polynomials and series. Is this little dot 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 here? Is this a series or polynomial? It's the same rule. If it stops at a finite stage, this one stops at a finite stage. If it goes on forever, it goes on forever.
You can add up terms of x and z.
So, interesting question. So the question I was just asked is, I thought that a series added up finite numbers, you could add up x. That was what you said, right? Okay, now notice that I pulled that off on you by changing the letter a to the letter x at the very beginning of this commentary here. This is a series. For each individual value of x, it's a number. So in other words, by plugging in x plus a half, I get 1 plus a half plus a quarter plus an eighth, and I'll get a number which is 2. And I'll plug in a number over here, and I get a number. On the other hand, I can do this for each value of x. So the interpretation of this is a function of x. And similarly, this is a function of x. It works when we plug in the possible values of x between -1 and 1. So there's really no distinction there. It's just I slipped it past you. These are functions of x. And the notion of power series is this idea that you put coefficients on a series, but then you allow yourself flexibility is to power series. And that's exactly what we do. Okay, there are other kinds of series where you take other interesting functions and be like sines and cosines. There are lots of other series that people study. And these are the simplest ones. And all those examples are extremely helpful for representing functions. But we're only going to do this example. All right. So here are the two rules. And now there's only one other complication here, which I have to explain to you before giving you a bunch of examples to show you that this works extremely well. And the last thing I have to do for you is explain to you something called Taylor's formula.
Here we go. 39 minutes in.
Taylor's formula is the way you get from the representation that we're used to of functions to the representation in the form of these coefficients. When I gave you the function e to the x, it didn't look like a polynomial. And we have to figure out which of these guys it is if it's going to fall into our category here. And here's the formula. I'll explain to you how it works in a second. So the formula is f of x. It turns out there's a formula in terms of the derivatives of f. Namely, you differentiate n times and you evaluate it at 0. And you divide by n factorial and multiply by x to the n. So here's Taylor's formula. This tells you what the Taylor series is. Now, about half of our job for the next few minutes is going to be to give examples of this. But let me just explain to you why this has to be. If you pick out this number here, this is the an, the magic number an here. So let's just illustrate it. If f of x happens to be a0 plus a1x plus a2x squared plus a3x cubed plus dot dot, and now I differentiate it, right? I get a1 plus 2a2x plus 3a3x squared. If I differentiate it another time, I get 2a2 plus 3 times 2a3x plus dot dot. And now a third time, I get 3 times 2a3 plus etc. So this next term is really in disguise 4 times 3 times 2x. I'm sorry, that would be 4x. That's what really comes down if I kept track of the fourth term there. So now here is my function. But now you see, if I plug in x equals 0, I can pick off the third term. F triple prime of 0 is equal to 3 times 2 times a3. Right? Because all the rest of those terms when I plug in 0 are just 0. So here's the formula. And so the pattern here is this. And what's really going on here is this is really 3 times 2 times 1. A3. And in general, an is equal to.
Okay, let me switch back, and I'm going to rewrite how I did this because I'm not wrong, but I was just kind of glossing over some things that were important for that. So Okay, so I think that one's good. Let's go over to this other one, which was going to be, I think this is going to be inverse substitution. I don't know whether I want to watch a little bit first because I think this might be a little different than the thing I'm thinking it is. So I want to watch it a bit first to see whether I'm right about it. Now, I've done these classes before, so that's why I'm kind of watching them faster, because this is mostly just a reminder for me.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit
So I'm going to be about trig integrals and trig substitutions. This is maybe the most technical part of this course, which maybe is why Professor Jarrison decided to just take a lead, go AWOL just now, and let me take over for it. But I'll do my best to help you learn this technique, and it'll be useful for you. So we talked about trig integrals involving sines and cosines yesterday. There's another whole world out there that involves these other trig polynomials, trig functions, secant and tangent. And let me just make a little table to remind you what they are, because I have trouble remembering myself, so I enjoy the opportunity to go back and remind myself of this stuff. Let's see, secant is 1 over one of those things. Which one is it? It's weird, it's 1 over the cosine. And the cosecant is 1 over the sine. Of course, the tangent, you know, is the sine over the cosine, and the cotangent is the other way around. So when you put a co in front of it, it exchanges sine and cosine. Well, I have a few identities involving tangent and secant up there in that little prepared blackboard up above. Maybe I'll just go through and check them out to make sure that we're all on the same page with them. So I'm going to claim that there's this trig identity at the top, secant squared is 1 plus the tangent. So let's just check that out. So the secant is 1 over the cosine, so secant squared is 1 over cosine squared. And then whenever you see a 1 in trigonometry, you always have the option of writing it as cosine squared plus the sine squared. And if I do that, then I can divide the cosine squared into that first term, and I get 1 plus sine squared over cosine squared, which is the tangent squared. So there you go. That checks the first one. That's the main trig identity. Talk about today. That's the trigonometry identity part. How about this piece of calculus? Can we calculate what the derivative of the tangent of x is? Actually, I'm going to do that on this board. Well, so the tangent of x is sine x divided by cosine x. So I think I was with you when we learned about the quotient rule, computing the derivative of a quotient. And the rule is you take the numerator and you take the derivative of the numerator, which is cosine, and you multiply it by the denominator, so that gives you cosine squared. And then you take the numerator, take minus the numerator, and multiply that by the derivative of the denominator, which is minus sine x. And you put all that over the square of the denominator. And now I look at that, and before my eyes, I see the same trig identity, cosine squared plus sine squared is 1, appearing there. This is 1 over cosine squared of x, which is secant squared. And good, so that's what the claim was. The derivative of the tangent is the secant squared. That immediately gives you an integral, namely the integral of secant squared is the tangent. That's the fundamental theorem of calculus. So we verified the first integral there. Well, let's just do the second one as well. So if I want to differentiate the secant, the derivative of the secant, so that's d dx of 1 over the cosine. And again, I have a quotient. This one's a little easier because the numerator is so simple.
So I take the derivative of the numerator, which is 0, and then I take the numerator, I take minus the numerator times the derivative of the denominator, which is minus sine x, and put all that over to the square of the same denominator. So one minus sine came from the quotient rule, and the other one came because that's the derivative of the cosine. But they cancel the sine over cosine squared, which is sine over cosine times 1 over cosine, and so that's the secant, that's 1 over cosine times the tangent. So, not hard. That verifies the derivative of the secant is secant tangent, and it tells you that the integral, that weird thing, in case you don't want to know, the integral of the secant tangent is the secant. Well, there are a couple more integrals that I want to do for you that where I can't sort of work backwards like that. Let's calculate the derivative of let's calculate the integral of the tangent. Just do this straight out. So the tangent is the sine divided by cosine. And there's a habit of mind that I hope you get into. When you see a cosine and you're working in and try calculating an integral like this, it's useful to remember what the derivative of the cosine is, because maybe it shows up somewhere else in the integral. And that happens here. So that suggests we make a substitution. U equals the cosine of x, which means d is minus the sine of x dx. That's the numerator. Minus sine. And so I can rewrite this as, under this substitution, I can rewrite this as minus du. That's the numerator. Sine x dx is minus du divided by u. Well, I know how to do that integral too. That gives me the natural log, doesn't it? So this is minus the natural log of u plus a constant. I'm not quite done. I have to back substitute and replace this new variable that I made up called u with what it is. And what you get is
Let me keep watching here.
Minus the natural log of cosine of x. So the integral of the tangent is minus log cosine. Now, I don't, you find these tables of integrals in the back of the book, things like that. I'm not sure how much memorization Professor Jerison is going to ask of you, but there is a certain amount of memorization that goes on in calculus. And this is one of the kinds of things that you probably want to know. Let me do one more integral. I think I'm making my way through a prepared board here. Let's see. Good. So the integral of the tangent is minus log cosine. I'd also like to know what the integral of the secant of x is. And I don't know a way to kind of go straight at this, but let me show you a way to think your way through to it. If I take these two facts, tangent prime is what it is, and secant prime is what it is, and add them together, I get this fact that the derivative of secant of x plus tangent of x is, well, it's the sum of these two things, secant squared plus secant tangent. And there's a secant that occurs in both of those terms. So I'll factor it out, and that gives me, I'll put it over here. There's the secant of x that occurs in both terms. And then in one term, there's another secant, and the other term is tangent. So that's interesting somehow because the same term appears on both sides of this equation. Let's write u for that secant x plus tangent of x. And so the equation I get is u prime equals u times the secant of x. I just made a direct substitution just to decide that I'm going to write u for that single thing that occurs on both sides of the equation. So u prime is on the left, and u times secant of x is on the right. Well, there's my secant that I was trying to integrate, and what it tells you is that the secant of x is u prime divided by u. Just divide both sides by u, and I get this equation. U prime divided by u, that has a name. I'm not sure that Professor Jackson's used this in his class, but u prime over u, we actually use something like that. It's on the board right now. It's a logarithmic derivative. It is the derivative of the natural logarithm of u. And it's easy to read this from right to left. If I want to calculate the derivative of the logarithm, well, the chain rule says I get the derivative of u times the derivative of the log function, which is 1 over u. So often u prime over u is called the logarithmic derivative. But it's not what I wanted because it's expressed the secant as a derivative. And I guess I should put in what u is the secant plus the tangent. And so that implies that the integral, integrate both sides, that says that the integral of the secant of x dx is the natural logarithm of the secant of x plus the tangent of x. So that's the last line in this little demo that I created that we can use now for the rest of the class. Okay, any questions about that trick? It's a trick. I have nothing more to say about it. Okay, so the next thing now I want to make the point that using these rules and some thought, you can now integrate most trigonometric polynomials, most things that involve powers of sines, cosines, and tangents, and secants, and everything else. For example, let's try to integrate the integral of secant of fourth of x, big power of the secant function. Well, there are too many secants there for me, so let's take some away, and I can take it away by using that trig identity, secant squared is 1 plus tangent squared. So I'm going to replace 2 of those secants by 1 plus tangent squared. That leaves me with 2 left over. Now, there was method to my madness, because I got a secant squared left over there, and secant squared is the derivative of tangent. So that suggests a substitution. Namely, let's let u be the tangent of x, so that du is secant squared of x dx. And I have both terms that occur in my integral sitting there very nicely. So this is the possibility of making the substitution and seeing the secant squared appear as part of the differential here. That's why it was a good idea for me to take 2 of the secants and write that as 1 plus tangent squared. So now I can continue this. Under that substitution, I get 1. Well, yeah, and I should add the other fact that, well, I guess it's obvious that tangent squared is u squared. So we get 1 plus u squared. And then du, the secant squared of x plus x times dx, that is du. Well, that's pretty easy to integrate. So I get u plus u cubed over 3 plus a constant. And then I just have to back substitute with things back in terms of the original variables. And that gives me tangent of x plus tangent cubed. And there's the answer. So we can spend a lot more time doing more examples of this kind of polynomial trig thing. It's probably best for you to do some practice on your own. Because I'm going to talk about other things also. And what I want to talk about is the use of these trig identities in making really trig substitution integration. So we did a little bit of this yesterday, and I'll show you some more examples today. Let's start with a pretty hard example right off the bat. So this is going to be the integral of dx over x squared times the square root of 1 plus x squared. Okay, it's a pretty bad looking integral. So how can we approach this? Well, the square root is the ugliest part of the integral, I think. What we should try to do is write the square root in some nicer way. That is, figure out a way to write 1 plus x squared as a square. That'll get rid of the square root. So there is an example of a way to write 1 plus something squared in a different way. And it's right up there. Secant squared is 1 plus tangent squared. So I want to use that idea. And when I see this form, that suggests that we make a trig substitution and write x as the tangent of some new variable, which you might as well call theta, because it's like an angle. Then 1 plus x squared is the secant squared, according to that trig identity. And so the square root of 1 plus x squared is the secant of theta. Right? So that's the reason, this identity is the reason that the substitution is going to help us, because it gets rid of the square root and replaces it by some other trig function. I better be able to get rid of the dx too. That's part of the substitution process. But we can do that because I know what the derivative of the tangent is secant squared. So dx d theta is secant squared theta. So dx is secant squared theta times d theta. So let's just substitute all that stuff in and rewrite the entire integral in terms of our new variable theta. So dx is in the numerator, that's secant squared theta d theta. And then the denominator, well, it has an x squared, that's tangent squared theta. And then there's this square root, and we know what that is in terms of theta. It's secant of theta. Okay, now we've done the trig substitution. I've gotten rid of the square root. I've got everything in terms of trig functions, so the new variable. Pretty complicated trig function. This often happens. You wind up with a complete scattering of different trig functions in numerator, denominator, and everything. A systematic thing to do here is to put everything in terms of sines and cosines. Unless you can see right away how it's going to simplify, the systematic thing to do is to rewrite in terms of sines and cosines. So let's do that. So let's see, the secant squared, secant is 1 over cosine. So I'm going to put a cosine squared in the denominator. Oh, I guess the first thing I can do is cancel. Let's do that. That's clever. You were all thinking that too. Cancel those. So now I just get 1 cosine in the denominator from the secant there in the numerator. It's still pretty complicated, secant over tangent squared, who knows? Well, we'll find out. Because the tangent is sine over cosine, so I should put a sine squared where the tangent was, and a cosine squared up there. And I still have d theta. And now you see some more cancellation occurs. That's the virtue of writing things out in this way. So now the square here cancels with this cosine, and I'm left with cosine theta d theta divided by sine squared theta. That's a little simpler, and it puts me in a position to use the same idea I just used. I see the sign here. I might look around in this integral to see if its derivative occurs anywhere. The differential of the sign is the cosine. And so I'm very much inclined to make another substitution, say u, direct substitution this time, and say u is the cosine of theta, because then du, say u is the sine of theta, because then du is cosine theta d theta. And then this integral becomes, well, the numerator just is du. The denominator is u squared. And I think we can break out the champagne because we can integrate that one finally, get rid of the integral sign. Yes, sir? Okay, how do I know to make u equal to sine rather than cosine? Because I want to see du up here. If I had a sine up here, that would be a signal to me that maybe I should say let u be the cosine. Okay. Also, because this thing in the denominator is something I want to get rid of, this in the denominator, so I'll get rid of it by wishful thinking and just call it something else. And it works pretty well in this case. Wishful thinking doesn't always work so well. But so I integrate u to the minus 2 du, and I get minus 1 over u plus a constant, and I'm done with the calculus part of this problem. I've done the integral now, gotten rid of the integral sign. But I'm not quite done with the problem yet, because I have to work my way back through 2 substitutions. First this one, and then this one. So this first substitution isn't so bad to get rid of, to undo, to back substitute, because u was just the sine of theta. And so 1 over u is, I guess a fancy way to write it is this cosecant of theta. Right, 1 over the sine is the cosecant, so I get minus the cosecant of theta plus a constant. So a question in the back, yes, sir? I'm sorry, my hearing is so bad. How did I know this substitution in the first place? The only thing so it's because of the 1 plus x squared, and I want to make use of the trig identity in the upper left-hand corner. I'll make you a table in a few minutes that will put all this in a bigger context, and I think it'll help you then. Okay, I promise. So what I'm going to try to talk about right now is how to rewrite a term like this, a trig term like this, back in terms of x. So I want to undo this trig substitution. This is a trig sub. And what I want to do now is try to undo that trig sub. I'll show you a general method for undoing trig substitutions. This happens quite often. I don't know what the cosecant of theta is, but I do know what the tangent of theta is. So I want to make a relation between them. Okay, so undoing trig subs. So let's go back to where trigonometry always comes from, this right angled triangle. The theta in the corner. And then these three sides, this one's called the hypotenuse, this one's called the adjacent side, and that one's called the opposite side. Now, let's find out where x lies in this triangle. Let's try to write the sides of this triangle in terms of x. And what I know is x is the tangent of theta. So the tangent of theta, tangent of this angle, is opposite divided by adjacent. Did you learn SOHCAHTOA? Okay, so it's opposite divided by adjacent is the tangent. So there are different ways to do that, but why not just do it in the simplest way and suppose that the adjacent is 1 and the opposite is x? This is correct now, isn't it? I get the correct value for the tangent of theta by saying that the lengths of those are 1 and x. And that means that the hypotenuse has length 1 plus x squared. Well, here's a triangle. I'm interested in computing the cosecant of theta. Where does that appear in the triangle? Well, let's see. The cosecant of theta is 1 over the sine, and the sine is opposite over hypotenuse, right? So the cosecant is hypotenuse over opposite, right? And the hypotenuse is the square root of 1 plus x squared, and the opposite is x. And so I've done it. I've undone the trig substitution. I figured out what this cosecant of theta is in terms of x. And so the final answer is minus the square root of 1 plus x squared over x plus a constant. And there's an answer to the original problem. Okay. Good work. So for this, illustrate some things. Illustrated the use of trig substitution in a second. I illustrated patience. I illustrated rewriting things in terms of sines and cosines, and then making a direct substitution to evaluate an integral like this. They're different. Let's do 1 squared. That's the tangent of.
Where was the where was the what was the identity he used?
Right. So that's the way, reason this identity is the reason that the substitution is going to help us, because it gets rid of the square root and replaces it by some other trig function. I better be able to get rid of the dx too. That's part of the substitution process. But we can do that because I know what the derivative of the tangent is secant squared. So dx d theta is secant squared.
What was our I'll just write down here simply. Maybe I'll leave that here. Yeah, I think I'm going to leave that here for right now. Where am I? So I'm going to take a little break now. It's almost noon. When I get back at it, I think there's a few more things I wanted to work on. So I'll take a bit of a break, then come back this afternoon. Some of the things I wanted to, so let me just put little crosses through here. So Taylor extension, substituting variables. I did not do changing the order of integration. I don't know whether that was, yeah, that's a multivariable calculus. I didn't download any lecture for that. And integrating by parts. I think maybe I want to go through some of the lectures again on some of these concepts that were hard. So, oh yeah, we've done this now. Yeah, if I were going to spend some time, and I'll shift so you can see what I'm writing here. If I were going to spend some time, it would be on these guys here, which are actually from 804, which I didn't feel like I had a good intuition about. Delta function normalizability should be pretty simple. It just kind of went over my head in the class. Commuting through, I feel like I understood that fair enough now. Yeah, the adding zero. This is like a skill, but I think that's going to get practiced again. I don't think limits are going to be a problem here. Order of integration is maybe something else to look at. I don't think it came too often. I think there's been one or two problems that used it. I think so. The K is related to the wave number, so I think that's what is it? 2 pi, right? So that was a kind of key fact. Yeah, so these ones are short ones, so I should be able to do these ones. So maybe I'll work on doing these 3 as quick Feynman techniques, and then work on the rest of the afternoon doing this. And maybe I will download. I'll look right now to see before I sign off right now. I will look right now to see if there's anything on changing the order of integration from 1802. Lagrange partial different double integral. Change of variables. This might be it. You know what? I will download it anyways. And what else do we have? Is there anything else from? No, I think I'm good on that then. So let me just go back here. So I might have time to do these. I think if I'm going to focus on stuff, I'm going to focus on these, which are 804 concepts, and not on this 1802 concept, because it only came into place in one thing, and I feel like it's not changing the order of integration. I mean, it's useful, but I don't know whether that's going to be where I want to spend my time. So I think when I come back, I'm going to do these 3 guys. Do Feynman techniques for those, get these down, and then I will, I think that I will be pretty good with these. I have my kind of fuller fuller list of concepts to do Feynman's for. So I might be adding to this. This is not necessarily to say when I cross these things out, it's not necessarily even to say that I've done them, that like they're done. I don't need to do any more work. Good about it. So what I'm probably going to do is do these small Feynman techniques and then work on these. This is about 4 classes, so I may not get it all done today, but it is applying to later problem sets. So if I switch to doing practice on Monday, I can focus on the earlier problems here. The ones that are circled, yeah, I think this is good. I feel good about doing this for the rest of the day, and then I'll be taking a break over the weekend, and I'll be back for like, it's gonna be my last like kind of full study week, and then there's gonna be 2 days where I'm probably just gonna be doing exam prep and then finishing the exam. So I will sign off for now, and I will be back in an hour or so.